Okay, so I think it's recording now.
Yeah.
Yeah, you can see it recording, right?
Yeah.
Okay, perfect. All right, this is take 3. So let's hope it gets recorded. So welcome. So Bruce and I are going to talk a bit about machine learning in practice today. So you're going to see some of our considerations, if you want to do your own machine learning project. A few examples, and as you can probably see by the intro, also some rambling. So this is me. So I'm Nemanja. Originally, I'm from Serbia. I studied computer engineering at the University of Aachen. Then I did some internship at Philips and essentially stayed there to do my PhD. PhD was in the area of speech communication. Actually, let me see if I can, okay, I can minimize this. So speech communication systems in realistic environments. Essentially, it was processing and understanding and making sense of various types of data: audio, speech, ultrasound, behavioral data, physiological data, and so on. Over the last 2.5 years, I worked in data science consulting, about half a year at Forkind, which is our current employer. And the tasks there, when I'm very lucky, include really cool DS and machine learning projects, or even some easier, data engineering projects, because I'm not a data engineer, but I can do a thing or two. The projects may also include some cool business development or project and team management. So I'll let Bruce introduce himself next.
Hi, I'm Bruce Ferguson. I'm Canadian, and I started out as a geophysicist. I was doing basically seismic imaging in Canada for Mobil Oil. And while I was doing that, I got bitten by the machine learning bug. It was a long time ago, and that used to be called computational intelligence at the time. I wrote my first neural net in 1990. And I've basically been applying some form of machine learning throughout my career. Once I started working with machine learning, I did a seismic pattern recognition program, which got me a bunch of attention and an assignment at the Dallas Research Lab. And it was pretty cool, but once you're able to predict porosity in the subsurface, you're basically imaging something that took hundreds of millions of years to form, and it's not going to change in our lifetime. So it got kind of boring, and after that, I pointed my models to the markets because they were very dynamic, constantly changing, and quite exciting. And I had a 17-year run in capital markets and investment management, basically spanning everything from technology to the trading side, and from both the sell and buy sides of the industry, and with holding periods that ranged from months down to sub-seconds. After that, I left finance and I moved over to Amsterdam, where I became a partner in, prior to that, I was working for KPN Data Science Lab as a senior data scientist and straddling 2 teams. That was a streaming engine team. I was basically a data scientist embedded in that team doing real-time machine learning. Subsequently, I left and became a partner in Forkind, Amsterdam, where I've been for about 1.5 years, and I'm doing machine learning consulting.
All right, thank you, Bruce. So now the question is, like, why are we all here today, and why did we spend such a long time introducing ourselves? So this was not to brag, and in my case, there's also nothing to brag about. This was more to highlight one thing, and namely how useful it is going to be for you to understand these theoretical concepts of machine learning and be aware basically of all the different methodologies within the field. So it's a very vast field and it's developing rather quickly, so you cannot learn everything. Probably the way it's going to work out for you if you decide to stay in the field is you either going to focus on an area that you're really interested in, likely in research or maybe a research organization, since you're in Eindhoven, maybe Philips or ASML, Or you might do something like Bruce and I are doing, consulting, where essentially the area that you focus on is going to be determined by the problem that you're trying to solve. But in any case, these methods are super useful and they're very transferable. You can use them in no matter what field you end up in. You'll see later, even if you do something like arts and design, still can be very useful. Originally, when I talked to Joaquin about giving this talk, the idea was, to talk about this. So this is the AI Whisky that our company 4Kind designed. Well, we designed an algorithm that essentially created the recipe for this whiskey. But then we decided, okay, apart from this practical case, maybe we can also talk a bit about some practical considerations. What happens if you want to run machine learning algorithms in practice? Maybe if you want to create your own app or your own product, or maybe even create a machine learning business. And then this whole Corona thing happened, and now we're all in isolation, and you're all very smart students, as I heard. So what we thought of doing is essentially going to give you a little bit of detail about a lot of things. So the hope here is that you get some inspiration from all the examples that we provide. And with the examples, we also tried really to provide, reading resources, so you can dig deeper if you're interested in that specific area. And then maybe you can do something cool at home now, since, you have time. And there's even going to be one movie recommendation as well. And overall, I think Bruce and I went a bit crazy with the number of slides here. So at some point, we'll see, maybe we start going through things a bit faster. But without further ado, let's get started. So first, some practical consideration for running machine learning projects in practice. No specific order, but I guess the most basic thing that you can start with is what problem are you really trying to solve? Because what we've seen a lot with our clients, is sometimes the question, like what problem is being solved and why it's being solved, is not being asked. So I worked a lot in data science in marketing consultancy companies. So I have a lot of examples from that. One pretty famous one in marketing is the area of attribution modeling. So what attribution modeling is, let's say you have a website, you sell a product. People come to your website different ways. So you can send them an email with a discount, they click on that, then your entry channel is email. They can search for you on Google, and they have these like paid search ads, then your entry channel is like paid search, and so on. So you have different channels. And a lot of businesses, especially marketing directors, wanted to know, okay, can you model and attribution, meaning that can you tell me how much each channel is responsible for my conversions? And then the question that we always ask, okay, but what do you want to do with that information? And the answer that we almost always got is allocate marketing budget. But then if you go a bit deeper and ask them, okay, let's assume I have a model and it allocates a certain percentage to a certain channel, what do you do with that information? And then they realize that the question is actually wrong, because you cannot simply use that information to allocate your marketing budget, because different marketing channels have different costs. It's not a linear relationship between how much you put into a marketing channel, how much you get out, because otherwise you can just pump millions into one channel and get additional money. So this is an example of a question framed poorly. Some of you might also, you might be entrepreneurs and you want to start your own business, maybe focused around machine learning. I did something like that some time ago, and I also know quite a few startups who went through this so-called startup boot camps, essentially where the people that run the boot camp try to make you investment ready. And most of the startups, more than 90% during that boot camp, they pivot. So that means they change what they originally want to do. And here you have kind of a similar problem, that the question was incorrect. So basically, or you didn't ask it, like, what do people really want? What does the market really want? Is this the correct question that I'm asking now? In most cases, it's not. And especially for us engineers, it's a bit tricky. You have these like interesting ideas and all this cool stuff, and you think people are going to go crazy over it. But unfortunately, in a lot of cases, it's the simple or even the stupid ideas that succeed and get funded. And then finally, there's also another story. If you want to do machine learning in practice, you also have to make sure that the people you approach or the businesses you approach are open for it. So you saw the whiskey examples, and I kind of tried to sell a similar thing to a French winemaker, and yeah, they weren't too enthusiastic about it. So that's about the question. The second question is, do you really need machine learning to solve the problem or the question that you identified? So here I linked a document, about the rules of machine learning from a Google person. Highly recommend you go through that. And actually, the first rule is don't be afraid to, not use it, to just use simple heuristics. Because this is also something we see a lot in practice because, machine learning or AI is really hot. Everyone wants to use it, but is it really needed? So here in this example, data scientist was tasked with predicting the channel someone contacts you in. So do people contact you via email or phone or, a subscription forum or something else? And to create a prediction algorithm for that, where the simple solution is simply, just, collect the correct channel information initially. So you don't need the project at all. Then another problem that we often encounter, and this is a real one, is over complex projects. So in this project, essentially, we had a customer who has a production plant and they wanted to link characteristics of the production line to the end product and its imperfections. And the way they wanted to collect the data was by taking photos of the end product. And then one request at the end was, okay, but since we're going to take photos by different people, different times of the day, different devices, and so on, can you also build a pre-processing step for your algorithm to take care of all of that? And sure, you can do that. There's algorithms to pre-process images, but why? You can also just standardize the way you take photos, so there's no need for that. The next, important consideration is, whether you have enough data for actually building your machine learning algorithm. There's a lot of examples where the data that you have is not really useful. One that I encountered a few times was basically where businesses want an anomaly detection or an anomaly prediction algorithm, but then ultimately they don't collect the anomaly data because they know it's wrong, so they just throw it out, which is a rather silly example, but it really happens. Another one from marketing is that you sometimes have data, or you can have a lot of data, but it's extremely noisy and extremely difficult to work with. So in the example that I gave you before with the attribution modeling, you kind of want to see, okay, which marketing channel is responsible for my sales? What that requires you to do is have the so-called customer journey. So, you browse on the web, let's say we talk about ball.com. You go to ball.com, you come either by organically searching, you come from an ad, you come from a display ad for something. All these touch points with ball.com make up your customer journey. And in the ideal case, that's data that you would have, and then you would do your modeling. However, what happens in the real world is that this data is extremely messy, because if you use multiple devices, your phone and your computer, those two are not connected, so you will be logged as two different users. If you clear your browsing history, or if you, disable cookies, also these sessions will not be logged. And you have these, advertising monopolies. So if you're on Facebook, click on an ad, and if you do the same on Google, Facebook and Google don't talk to each other. So the data is just from the get-go extremely messy, and this is something that you need to think about if you actually plan to use this data to achieve a specific goal. The next one. So let's say now we talk a bit about the data and about the algorithm or the question. But let's go a bit beyond that. So about the technical constraints. So this is something that's, people often don't think about. This may not be such a big deal, for example, in research, but if you want to build your own app or build your own product, it's definitely important. And first, you can have a disconnect with business if you're, let's say, working as a consultant and you want to build a classifier for whatever, and they expect 100% accuracy at all times. That's just simply the misalignment in the expectations. But let's talk about a more famous example here. So you might have heard about this. So the Netflix prize. Essentially, what this was is that Netflix ran a competition in 2009, I think, for people to build an algorithm that best predicts the score of a movie. So how much a viewer is going to like a movie. And it was a big deal because it was, I think, $1 million reward. And I linked the article here to the winners. There was a lot of impressive algorithms, but ultimately what happened then is that Netflix never really employed this algorithm. So they spent $1 million, but they never really put it into production because the engineering costs were simply not worth it. Because the algorithm was created from a standpoint, of like making the best algorithm possible, but not thinking about putting it into production. And that's also something that you may not face as much if you do university courses or courses on Coursera, or maybe even if you do research. But if you at some point really want to have something that's running in production, these are things that you need to think about. And at this point, maybe it's also useful to briefly mention the cloud. So, you can always run algorithms on your computer. That's completely fine. But again, if you want to have an app or like a finished product, it will likely have to run on the cloud. So, and nowadays, storage and processing power are quite accessible and quite cheap. So this is an example from the Google Cloud Platform. So this is by no means an advertisement of Google. So, use Azure, AWS, whatever you want, but, just be careful. An example here is where I can spin up a virtual machine with 16 CPUs, 60 gigabytes of RAM, and that costs me about 48 euros a month. Now, this 48 euro is essentially if you use this 24/7. So if you're running some sort of, more intense processing, I think in the course, the last couple of lectures that you've seen were in the area of deep learning. So I'm assuming that you ran into some issues with, training and waiting times there. If you want to try these things out on the cloud, you can do that. And these 48 euros is also not really what you pay, because you can just simply spin up the virtual machine and close it whenever you're using it. And therefore you can cut down on cost. If you have reoccurring jobs, you can also do a bit more funkier things by, scheduling jobs that will basically start the virtual machine, run your program, and then close it. And the nice thing about this is that, since you're all students, you'll have some free credits to start, some student discounts, and, regardless of whether you're a student or not, there's always free credits. I think GCP gives you about $300 when you open an account. And why would you use the cloud? Well, because of the speed of development, and you can get everything, you can get all the resources in seconds. You don't need to worry about any setup. A lot of the services are managed, so it's on Google to do these things. I mean, if you're a developer and if you're into setting all these things up by yourself, it's fine. But if you just want to save time and run an algorithm and see what it does, then you can do it in the cloud rather easily. And they enable you to auto-scale. Auto-scale essentially means that you really use the processing power that you need. So in case your needs start increasing, the cloud provider basically provisions you with additional processing resources. If the processing power needs start decreasing, they free up some of the resources so you don't pay as much. And yeah, there's a lot of tutorials and learning resources online. But as with everything, you still need to be careful, and you need to know what you are doing. So what we see, or what I've seen a lot in previous projects I work in, is a lot of companies, when they get started out with with doing data science or doing machine learning, they don't actually need a data scientist; they need a data engineer. And you as well need to make sure that either you or someone in your team knows what they're doing, because otherwise you can run into problems like this. So, in the first example is from a former client that have their product running in the cloud. It was set up by an administrator that then left the company, so nobody knows what was set up and everything. And then essentially a software update came in, as it often happens, which meant that if the software or if the setup was not changed, the jobs would start failing. And if jobs failed, this was essentially the main product of that customer, so they would not be able to service their clients. And then you start tracing the administrator mailing what has been done, what has not been done, and so on. So that's always quite messy. And the second example is actually a pretty funny one. Well, I guess not for the guy. So we had, from a client, we had a business person that was interested in learning about stream processing, which is fine. And they essentially found a tutorial, set up a process on the cloud. But then I guess they got bored. They forgot to close the job, enabled auto-scaling, and left on vacation. And if you just enable auto-scaling and don't set any parameters, the cloud provider may actually provision as many resources as they're needed. And due to an error in his setup, what ended up happening, he spun up, I think, around 700 virtual machines and incurred about 80K in cost in about 10 days. And I randomly noticed it while checking some billing receipts in the account. So don't do this. I mean, we fixed it with the cloud provider, so they returned the money, but still, it's quite scary. So be careful still when setting these things up. All right. So the next point, just take a sip of water. All right. So the next point is about proof of concepts. And this is something that I think may not be apparent from when you're initially getting into the field. But, unfortunately, I would say in machine learning projects, the actual modeling part is the smallest part of the project by far. These percentages may not apply in research, so it might be a bit different if you're really focusing on optimizing an algorithm. But if you want to put something into production, usually this is the split. So in that case, it's actually really important to start working with proof of concept, meaning that you build something small and simple and test its effectiveness and whether everything works fine. And this is also a methodology that we apply at Fourkind. So we also have a proof of concept, build an algorithm, see whether it addresses the problem, and then we go into the whole engineering part and setting up the infrastructure and everything. And it's always like the same, the clients always wonder, why is this a machine learning project? And 80% of the cost is not machine learning. So this is the reason. And again, highly recommend, if you have time, to go through these two articles that are linked here as well that talk about this in a bit more depth. The next part is, talking about failures of machine learning projects. And I think this you probably also heard during the previous lectures in your course. Essentially, feature engineering is, the core of machine learning. And it's usually the reason why projects fail. And a good rule is to always, start with good feature engineering, use a simple algorithm rather than, a sophisticated algorithm without doing any proper feature engineering. And again, an article that goes into this in a bit more depth, but what I really wanted to share is this, feature tools tool. So it's essentially a Python library for automated feature engineering. So I recommend, if you have time, again, check it out, try out some of the tutorials. There's quite a few, and see whether you can incorporate it in your pipeline. All right. So the next step is then, so let's say you've built the algorithm, you've set up your infrastructure, and then what? So then your algorithm is running, it's in production, but it might have to update, or how do you monitor its health, or how do you monitor the performance? So first thing that you need to do is define a metric. So what are you measuring? And this is something that I've encountered quite a bit in the past, where the metrics are either ill-defined or don't really make sense. For example, we had clients where they requested recommendation systems, and the metrics there were, for example, how often certain items are clicked on, which may seem fine. You recommend an item, it gets clicked on, but ultimately, what do you really care about? You care about whether people spend money. So ideally, that should also be your metric. Another example is the conversion rate. So I've seen at least 5 or 6 definitions of conversion rates, depending on whom you talk to. It can be people buying a product, which it should be in my eyes. It can be adding to cart. It can be clicking on enough things on the website, subscribing to a newsletter, and so on. And the question here again is like, what problem are you trying to solve? Like, what matters here is, do people spend money? And then in my mind, that's also what you should be measuring. Then the next point is talking about adaptations of your model. So what you usually do when you put a model into production, and you get additional data, and then at some point you will retrain your model. But here you have to be really careful with what you're doing. And here also, again, I say I recommend everything, but I really recommend this article by a colleague of us called the Unlearning Machines. And this is something we've observed quite a bit in practice. And I'll give an example here. So you're tasked with building a churn prediction model. So essentially, for any client, churn is very expensive. It's cheaper to keep your existing clients than to get new ones. So churn prediction is quite interesting. You build a model. The model is live. And then you have some sort of, procedure. Let's say the top 10 of the identified churners, your customer service will contact. Let's say I'm one of them. You contact me, and I decide, okay, no, I'm not churning. I'm staying. And then what often happens, then on the next day, the whole algorithm gets retrained on this new data. But essentially, you've unlearned the original signal because I was associated with churning, and I would have churned, but you changed that outcome. So now essentially you have features that are associated with churn, where the label is not churn. And over time, this can basically lead this can basically destroy the performance of your algorithm. So you have to be careful about how you set these updates up. Then some additional considerations. Depending on what type of product you're running, what algorithm you have in mind. There's big differences between batch and stream processing. So if you're doing stream processing, real-time processing, it's important that you react to all the new incoming data. So then the algorithms can be a bit, less complex, and how you set up your infrastructure is much more important. Here again, I linked an article that talks specifically about that. And another concept that I think is quite interesting is concept drift. So what that means is that the relationship between the input data and the target variable changes over time. A good example there is spam filtering. So spam filtering is basically binary classification. Is it spam, not spam? But over time, you will accept, emails from more email addresses. Your email behavior will change. Spammers will get more creative and smarter. So with that, the spam filtering algorithm itself has to develop. So, one stupid example from my side was that, while I was doing my PhD, I was not receiving mails from Nigerian princes anymore. But after I finished the PhD, I started receiving a lot of spam from these random dubious companies wanting to, publish your work for money, of course, publish articles, get you to pay for some conferences, a visit, and so on. But with time, that also decreased. So I still get those emails, but now they're classified as spam. So it sort of has evolved over time. So that was kind of some of the considerations that we had in mind, and we can move on to the next, to the first use case, and that's Bruce's area of expertise. So you can go ahead.
All right, thanks. So I'm going to be talking about algorithmic trading, machine learning for algorithmic trading, but just to sort of set context, this is not something that I was hired into. It's something that I had to grow into. So it required sort of this path of heading through the technology side of things, understanding, all of the order flow and everything from a technology perspective on the sell side at a brokerage firm, before I could get to the point where I could understand what the requirements were for trading platforms to be able to do it algorithmically from a hedge fund. So with that in mind, I'll just go through some definitions to sort of frame things first. Algorithmic trading is basically automated trading. In this case, machine learning is the brains of the operation. It's deciding when to trade something, how much to trade. The buy side is hedge funds, pension funds, proprietary trading firms. And these are firms that are purchasing services from the sell side. The sell side is brokerage firms, investment banks, and they're providing services to the buy side. I've worked on both sides. The order book is basically the structure that holds the active buy and sell quotes for each stock. So this is anytime someone says they want to buy something at a price, it ends up on the book, unless it's a market order, and then it would get executed immediately. A brokerage fee is the cost incurred from crossing the spread to take liquidity. It's basically the cost incurred of trading aggressively. On the other side of that is trading passively, and that's where you would get a rebate when the market comes to you. So now I'll go on to the next slide. This is something that like in this portion of these use case, I'm going to be sort of identifying some things that you need to keep in mind from an engineering machine learning perspective and in the real world. So you need to be really crystal clear about your requirements and your environment, and you need to burden your system accordingly. And what I mean by this is that you can build this amazing neural network that perfectly predicts the future, and given a data set, you are able to get 100% recall on everything, 100% accuracy, 100% precision, and it's like it's beautiful, but the problem is you can't do it in time, and or the environment is unstable, and so it's useless. So these are really, really important aspects of the system. So for high frequency trading, the predictions need to be lightning fast, so models should have as few computations as possible. So we're going for really, really simple models. However, you still need to be right most of the time. Otherwise, you're just going to be wrong faster, in which case you end up just bleeding money in terms of brokerage fees. The main message that I was trying to make here is that you need to simulate your production environment, and you need to burden your system the same way you would be disadvantaged in the wild. So it's not enough to take a static data set and create a model and expect that it'll work. The overall system with all of its latencies has to be part of determining the model or the strategy. So ideally you could study the median and peak latencies and work that into the strategy itself. And this is true for any latency sensitive use case. So things like, what is the travel time, transit time of the data coming in and the orders going out? That needs to be put into the system. That needs to be modeled. Or the timestamps need to be adjusted in the data so that you're looking at the realistic data that you would be able to see at that time. Sometimes we're talking about fractions of a second. What is the impact of your order size? If you put out a large order, you can't just have a system that's predicting everything well and doing really well at small size and then expect that you can just increase the size and not have an impact on the market. So these are also things that you can use machine learning to model. Latency leads to the requirement to have parsimonious models. This is Occam's razor, so it's like, as simple as possible, not too simple. If your trade is not a pure structural arbitrage play, which means, basically if the market goes out of whack and you're just trying to beat it back down to the average and take that difference, you need to focus on a sweet spot, and you need to know what your information ratio is the highest, and you need
Bruce,
to.
Which slide are you on at the moment? Because I don't know if I'm correctly
40.
switching. But what's on the right side? Buy side?
No, it's you need to be crystal clear.
Oh, that one. Okay. Okay, cool.
I will let you know.
Okay, cool.
Well, let's go to the next slide. So here's an example on the sell side. So this is a brokerage firm. So a client sends you a huge order. They send a huge order to a trading desk, and they say that they want to get VWAP, which is volume weighted average price. They basically want to get the price of the market. And basically they've got a large order and they want you to hide in the noise. And so you take that trade and that order and you spread it out over the day and use the volume of the particular stock or instrument, whatever it is, the instrument is, if it's futures or options. But you would basically try to mimic the volume that's traded in the market. But this is something that changes every day. So you might need to predict the volume itself, but you also need to try to predict the price and the direction of the price. Say you have a buy order and you're predicting that the market is going to go down. You want to buy as low as possible. So rather than buy now, you could defer some of that volume into the future. So you just take this volume that you're expecting to trade now and just delay it. And that would be an example of something that you could use to try to beat this VWAP price, or do as well as that price. So yeah, let's go to the next slide.
Yeah.
So on the buy side, for a hedge fund or a prop trading firm, you might have like a market making strategy. And this is, a market maker is someone who's got a fiduciary responsibility to trade both sides. They're there to offer liquidity. A market making strategy isn't the same. And this is why some of these meltdowns have been so bad, is that liquidity just disappears. You know, the market making strategies just say, I'm done, and they get out, but they leave the market makers with the bag. This strategy is basically something where you're trading both sides of the market simultaneously and trying to capture the spread. And you can use machine learning to try to tilt this or bias this spread in one direction or another. So if you get filled too much on one side, you're going to end up with an inventory that you're going to have to flatten, and you could probably flatten it at a loss. This is just another example. And just to let you know, like, our contact information is at the end. And if you have any questions about any of this, and feel free to contact us. I'm not going to go into too much detail on this. Let's go to the next slide. This is on the tech specs. So this was 10 years ago. So, you know, things have changed a lot in that time, a real lot. A lot of these things that you are able to work with now, I had to roll my own. And so, you know, some of these things that I'm talking about, they probably wouldn't make sense now, but at the time these were pretty leading edge. I had a 48 core server co-located on the New York Stock Exchange with a separate NIC card, so that if anything melted down in the system, I could still access it remotely. The reason it was important to access it remotely is you know, it's pretty hard for anybody to get onto that floor. And when I say floor here, what I'm talking about is a server farm. The stock exchange really is pretty much a server farm. So when you're talking about high frequency trading, the really important thing is to be fast and right. But in order to increase your speed, what it boils down to is that the firm with the shortest cable length, shortest fiber optic cable, will have a distinct advantage. And so the closer you are to this epicenter of this server farm, or the shorter your cables are, the better your position. So it becomes really, really hard to compete against large firms like Citadel, for example. So in this case, I chose Scala because Scala was safer than C++ in terms of potential meltdowns. One of the shops I was at had written their trading platform in C, and they had an automated hedging component to it. And something went haywire. They, through faulty pointer allocation, the system overwrote part of the other system. And rather than crashing, it gave the impression that it had taken on a very large position in a particular stock. Subsequently, this hedging component traded live shares against this fictitious position and actually put the firm into a margin call. So in a matter of seconds, it was an $11 million loss. So it becomes really, really important that the systems are stable, which at the time for me meant, well, I'm not going to get into this pointer allocation problem. So I went with Scala, and I chose Scala because primarily because of two things. It allowed me to use ACA, which was an actor-based model that allows you to do parallel and concurrent processing quite easily. But also it gives you immutable objects. So it's a lot safer. You know that your objects aren't going to be changed as they get sent around in the system. Let's go on to the next slide. So talking about data now. In this particular case, for high frequency trading, we've got the order book in which you can look at activity, imbalances, and patterns. We've got sector ETFs, which are exchange traded funds, which basically try to mimic the market or the sector that they're in by buying up the correct proportion of each of these and allowing people to buy shares in the ETF itself. So you don't have to buy the whole market. You can get a representation of the market. So you can compare your, whatever stock you're trading against this ETF or against other stocks in that group, and there's some data things that you can do there as well. Macroeconomic data, things like regime shifts, which can be really important if you're going from a really quiescent period into a really volatile period. Twitter feeds, RSS news feeds, and everything for chatter. So things just to sort of get a hint at volatility. A lot of these high frequency trades are basically volatility trades. If the market's dead, you're not going to make any money. The market needs to be really, moving. And what we really need is we need data that's going to provide information that's going to be orthogonal to other data that we've already got. Next slide is the order book. The order book is basically the structure that holds the bid and ask side quotes. So this is an example, just a very rough thing, that you've got the buy side, which is people trying to buy things at a low price, and sell side, people trying to offer things at a high price as possible. And you've got the spread, which is the difference between the two of them, the gap in between the two of them. If someone crosses the spread, that's basically a market order. And if someone, from the perspective of the person that's crossing the spread, from the perspective of someone that's receiving that cross, it's really a limit order that someone's come to you and they're taking your trade out. So it represents a snapshot in time of the order book. It's constantly evolving. There are billions of new cancel, replace, like acknowledge and rejection messages daily, as well as fills and partial fills. Each message basically alters the information in the book to some degree. In order to create some of the features required for algorithmic trading and to simulate trading, the order book needs to be reconstructed on for every instrument that's being traded on the side of the strategy. So this is literally recreating the market on our side in order to be able to do the modeling and the simulation. So it's really quite an onerous task. Next slide. This is just getting into some feature engineering. I'm just basically going to talk briefly about this. So we've got all this raw data. What do you do with it? You want to create some features. The order book imbalances can be an indication of impending directional move. So basically what this is if one side has a really big buildup, the other side's going to notice that and they're going to try to move away from it, because if someone's accumulating a lot of size on the buy side, that basically means people they really, really want to buy something, but the sell side wants to sell it for higher, and so they can move away. And they'll probably get people coming to them and be able to sell at a higher price. So this book pressure is an example of something that you can calculate. And this would be looking at n levels deep into the book and trying to compare the value of each of these trades versus the mid price, which is the average price between the bid and the ask, and the difference between the price and the mid. And then accumulating all of that and looking at the imbalance between the one side versus the other. Next slide, dimensionality reduction. So we get a lot of really highly correlated time series and co-integrated series in finance. So this is an example. This agglomerative hierarchical clustering is an example of a clustering tool that you can use that basically organizes data into similar time series. And by choosing a threshold or cutoff, you can cut and choose representative time series that are this much smaller set. And that's about it. Let's go on to the next slide. Correlation and scale. So one needs to think about how to mix features with different frequencies and what it means to respect to the forecast horizon. So the forecast horizon really needs to be commensurate with the sample interval in the data. So what this means is you don't take data that's sampled yearly and expect to be able to accurately get a good prediction for the next day. And just also in line with that is you don't take daily data and expect to be able to accurately be able to forecast a year out. So it really needs to be sort of something that allows relationships in the data that might exist, you know, these sort of lead lag relationships, any kind of seasonalities and things like that. So it needs to take those into account. So if you've got a whole bunch of different scales, you probably want to consider multi-scale approaches. And another thing in finance, and it's probably true in other areas that I haven't seen it yet, but as the frequency increases, the distribution becomes more leptokurtic or fat-tailed. So as you go higher and higher frequency, you get fatter tails, and so you get much more erratic behavior. And machine learning algorithms don't necessarily handle these distributions very well. They tend to sort of assume, I don't know if it's most of them, but I would say a majority of them probably do. They assume a normal distribution. So that's something that, you know, if you've got some very fat-tailed data, you might need to squash it in some way. And another thing to consider is that is this thing about Epps effect. So like if you've got two time series that are highly correlated at a low frequency, if you go to higher and higher frequencies, you sample, you know, you're at yearly sample interval, monthly, weekly, daily, you know, 1 hour, and then you go higher and higher frequency, this correlation falls apart. And that boundary at which it falls apart is basically described by the Epps effect. And so the sample interval is actually really important when looking at relationships and correlations. Next slide, volume binning. So high frequency trading is it's like if you trade too aggressively, you end up burning through a lot of costs. If you trade too passively, the market can move away from you, and this is the trader's dilemma. And so in order to try to deal with that, one thing is to try to be appropriately active, and volume binning is one way that you can do this. And volume binning sort of is a proxy for volatility. So the more volume that's traded, generally, the more volatile something is. What this allows you to do is basically select a volume at which you want to bin, and then you create a bin every time that volume is filled up. And what happens is that effectively it's making the algorithm wake up more when the volatility or the volume is higher, and then sort of become more sleepy when it's slowing down. And from an algorithm's perspective, it almost is like time dilation, like it stretches things out or it compresses them. The algorithm doesn't really know this when you do the volume binning, because it just sees regular bins coming in and it just acts accordingly. Next slide. Some machine learning. So I'm just going to go through an example. As I said earlier, it's really important to have fast algorithms, so they need to be simple. And so a lot of these kernel-based approaches are really quite good for that. If you get into some deep learning, you know, often you've got so many calculations to make that you'll never make it in time. So again, if latency is an issue, then these are considerations. There are a lot of choices of kernels that you can use in these linear and the parameter kind of neural networks, for example. The one shown here is a Bernstein polynomial, and you can increase complexity or decrease it, you know, depending on what your needs are. You can also use, you know, Gaussian sort of shaped things or fuzzy sets or whatever you need. Going to the next slide, building a parsimonious model. So this is an example of, you know, this formula at the top here is a somewhat chaotic thing. It's not too bad, but it's a little bit chaotic. And if you look at the black dots on the plot, you can see that they've got these sort of radial arms, and it's almost behaving like a distorted, warped, strange attractor. So you can imagine that this would be, in some spaces, this would be pretty hard to model. But using this this sort of kernel-based approach, you can do something, you can create something that's only got 6 degrees of freedom, which is great because not only will it compute things quickly, but you're a lot less likely to overfit when you get into out of sample. Your performance will be much better. Yeah, let's go to the next slide. The model induction. So this is an example of taking these kernels and sort of inducing a model. You can go through this slide at your leisure, but basically the gist of this is that you can create models through growing and pruning and driven by an objective function. And the complexity can be increased by inserting basis functions or by adding new features or tensors, but the information gained needs to overcome a penalty for complexity, which I'm going to show in the next slide. The cool thing is that you can end up with a partially connected model and handle this curse of dimensionality quite well. Let's go to the next slide. So next slide here is just an information criterion. Here I've got minimum descriptive length, and it's made up of two terms, one for a closeness of fit and the other for a penalty for complexity. And so if you, on the previous slide, we talked about, this model induction, driven by an objective function. Well, this would be an example of that. And so you can create a model, test it, see how well it did, and then try to change it, add some complexity to it. Can you get a model that's better or worse? Basically every single step you need to try to improve the model, either through growing it or pruning it. And there's some information that I can provide at a later date if you're interested. Let's go to the next slide. And this will be the last thing I'm talking about right now. Model induction gives you a lot of opportunities. It's actually pretty interesting if you do it as a systemic kind of thing. So you're not just creating a model that's generating predictions against a data set. You're creating a system that's altering the model itself. So you can create a model in the presence of existing models and try to minimize the correlation to it simultaneously or some other objective function, and come up with new strategies that basically infill where the performance of your existing strategy is falling down. Or you can use models to generate specific attributes in mind, like something like, for instance, something that favors large downside moves, like an early warning system, or create one that thrives on volatility more. But another thing you can do is to actually try to match performance of someone else's strategy and try to infer the information that they're trying to use. So effectively reverse engineering their strategy. And that's, I hand it back to you, Nemanja.
Okay, cool. Yeah, thanks a lot, Bruce. So yeah, that was the first use case we wanted to talk a bit about today. And Bruce also, he gave you a lot of details since he has a lot of experience in the area. And I'll use up the remainder of the time just to give you a few additional ideas of some projects that we have worked on, but also some interesting areas of machine learning that you might not have encountered during your current class, or maybe you have. The first one is generative modeling. And the idea behind it, well, from our business perspective, was to augment design processes and potentially also create new products. But what is a generative model? So essentially, a generative model describes how a data set is generated. So in terms of like a probabilistic model, and by sampling from that model, we can generate new data. So for example, if you have too little data available, that's an option that you can use to generate additional data. The things that you have seen so far probably mostly fall under, the discriminative modeling. A key difference here is having labels. So if you want an example, you can think about, building a classifier, which you feed some images of paintings, and essentially you want to, decide whether this painting is a Van Gogh painting or not. So it's a binary classifier. And this discriminative modeling then estimates essentially the probability of a label given a certain observation that you provided. But the generative modeling itself, it actually gives you the probability of observing that observation. So essentially, it can generate new paintings that mimic Van Gogh paintings, depending on how well you train the model. And speaking about that, a good generative model, it's firstly going to generate samples that appear to have been drawn from the original distribution, as I mentioned. But the other part, that's actually the more interesting part, is samples that are different from the observations that you use for your training set. Because if you just change one pixel in the image, that's not very impressive. It would technically be a new painting, but it's not really impressive. Now, where is this used? So you might have seen some of these. I mean, for sure you've seen some of these examples, all the deepfakes and all of that stuff. One example is hyper-realistic human faces created by NVIDIA Labs. They're called StyleGAN. You can have a look here. So these are all, these are not real people. They were all generated by the model. Another cool example is text completion, here done by the OpenAI group. Essentially what happens here is basically you provide a human-written prompt, and then essentially the model completes the story. And this story is not even that impressive, but you see here, it's the first try. So you can, if you go to the website, you can also check out some of them, which are, where they gave the model multiple tries. There is a Lord of the Rings one as well, where it writes like a whole, section of Lord of the Rings, non-existing section. So it's quite cool. So there's a lot of additional examples that you can look into. You probably heard about this one, this painting that's been sold for way too much money some time ago. You can mix different styles to create a new style. Some examples from real products is Nutella, for example, used generative modeling to change the design of their Nutella jars, and many more. This book here that I put on the right, I can highly recommend. I think you should probably have it in the TU library. It has a lot of examples, and it has examples with code as well, Python code. So I think that's quite cool. Okay, but then you remember that at the start of the talk, I showed you that AI Whisky model. So essentially, looking at these generative models, what we asked ourselves at Fourkind was, okay, can we create whiskey? Can we create a new whiskey recipe using generative models? So this is a video that I'll have to skip because the sound doesn't work. But if you get the slide deck afterwards, you can listen to it. Bruce and I haven't figured out how to do it. I guess 35 years of combined experience is not enough for Zoom. So, but anyway,
can't be an expert in everything.
Can't be an expert in everything, exactly. Okay, so how do you start this project? How do you go about creating a new recipe? Well, a couple of challenges that you need to overcome, or a couple of steps. The first one is actually to define your target. What is a good whiskey? Like, how can you measure that? Well, you can say, okay, I can just go and get some ratings from the internet. You can get customer reviews, but are these really reliable? For example, I'm not really that much into whiskey, and I wouldn't want anyone to use any information I give, about a whiskey. The only thing I can say is smoky. So you can look at customer reviews, but you can also look at expert reviews. So then that's another data source. You can look at things like award ceremonies, and essentially different types of sources to generate your performance metric. But of course, there is always an uncertainty with that, because experts may not have rated all of the whiskeys, all of the recipes that you have. Customers may not have rated all of the recipes that you have. There's different amount of ratings per recipe, and so on. So this is like your first challenge, is to define your performance metric. The second challenge is to build your generative system. And what are we talking about here? So essentially the way this works, so the whiskey recipe, it's a blend of different casks of whiskey. So you basically have to select a number of casks, and how much of each cask you want to include in your blend. So if you have 100 casks, essentially the job is to pick 1 to 20 of them. How much you will use in percentages, of course, should sum up to 100. But then you also realize, okay, you're a computer, you're an algorithm, you cannot taste, you have to do it in Python, and there's an infinite amount of possibilities. So it is quite a challenging problem. And one additional thing that I want to reiterate here, and I mentioned this already before, with like, you know, a generative model being a good model. What we didn't want to do is, you know, have, for example, this recipe that you see on screen here, and then change this, I don't know, by 1%, or, and, you know, remove 1% here, add 1% here. So we wanted to create something new, something that where the people at Makmura, the whiskey distillery, there were a recipe where they say, okay, we wouldn't have thought of that. And for this, we used generative adversarial networks, or GANs. So you might have heard about them already. So I think they've been described as the most you know, exciting idea in machine learning some time ago. And below here, you'll find, you know, a couple of the foundational papers of what, well, the first one is, and the second one is essentially a GAN tutorial. I highly recommend you to walk through that. Just a high level overview. Essentially, GANs are an architecture for training a generative model. And usually, I mean, not usually, they consist of two parts. So a generator and a discriminator, and they're sort of playing a game against each other. So the generator is creating samples that are intended to come from the same distribution as the training data. So if we have, let's say, whiskey recipes, that's the training data. So the samples should kind of mimic that distribution. Discriminator examines all samples that he gets fed from the generator, and from the generator, and also from, you know, an outside pool of real data. And essentially, it needs to determine whether they're real or fake. Discriminator learns using traditional supervised learning, and it's penalizing the generator from producing data that it deems fake. So the generator learns over time because it gets feedback from the discriminator. So the generator is penalizing for producing a sample that doesn't trick the discriminator, and discriminator is penalized for misclassifying. Okay, so here, just to give you, well, basically the same thing in a more compact overview. And the interesting here about this is the training. So how they're trained. Unfortunately, I cannot go into too much details now, also because of the time. But essentially, they are trained in separate training processes. And, you know, that's essentially what we wanted to do with the whiskey. And then the final step of this whole thing was to make sure that it works end to end. What does this mean? Well, you know, ultimately, when a whiskey makes it to the market, the product has to be approved by the master distiller. And that's this lady here, as you see in the photo. The man on the right is our colleague Jarno. And she has to approve every recipe that's going to come out of this distillery. And she's basically the creative expert part here in this diagram. So just to reiterate again, basically you have a starting step. So you can start generating a recipe from blank, or you can already give it some, you know, initial guidelines. There are some constraints when you're generating these recipes, because, for example, some of the casks are extremely, you know, valuable and expensive. So you cannot just use 50% of that for a blend. So there are constraints that come with the mixing. After the start, you know, you push the data off to the generator, and then, you know, the competition starts between the generator and the discriminator. The generator creates a new recipe through exploration, or by using, you know, predicted by using predicted ingredients or casks that would make sense to him. Sends that off to the discriminator. The discriminator provides feedback, and, you know, off they go. At the end, when the algorithm converges, the top N recipes are then given to the creative expert. Well, you know, N cannot be too much. You know, she also cannot take that much whiskey. I think in our case, it was 7. And she does a tasting and selects the one that then makes it to the market. And that was the one that you saw initially. Yeah, so again, some, you know, techniques that we used throughout this project are listed here. And again, a recommendation, if you have time, just check this book out. There's, you know, theory, examples, and code as well. And you can start playing around with GANs yourself at home. Yeah, I think we're already over time, so I'm just gonna go really quickly through this one as well, through you know, a reinforcement learning use case, because I saw that you had reinforcement learning in your introductory lecture, but I don't think, I mean, it's a big topic again, so I don't think that's something that is going to be covered in your lecture. Essentially, it's about an agent being in an environment, performing an action, and then getting a reward, positive or negative, for that action, and through that reward, learning over time, meaning that the idea of the agent. So the goal is to maximize the reward. Examples, games like chess and Go. And if you want to get into reinforcement learning, so here are some materials for that. There is a presentation about purely about reinforcement learning by a colleague of us, Max. So I can really recommend that. Of course, there's basic reinforcement learning literature. And what I would really do if you plan to, learn a bit more is get into David Silver's lectures at UCL. So essentially, he's the guy who worked on the algorithm that played against the top Go players in the world. And he's also very good at teaching, but I don't know if Joaquin has any additional recommendations in terms of learning resources. By all means, listen to him. But this was just one of my favorites. And here comes the movie recommendation. That's why I wanted to go through this last part, because I promised you this. It's essentially the documentary about AlphaGo. So how, the whole process went and how they challenged the top Go player in the world in Korea. It's free to watch. You can watch it on YouTube, I think. And it's very, very interesting also because of a specific move that the human player does. It's after that called the God move. So yeah, if you find some time, I would highly recommend going into this as well. All right, and now to the actual, use case for reinforcement learning. We actually employed it for quite a few times already. It's dynamic pricing. So what's dynamic pricing? Basically, you want to dynamically adjust the price of something you're selling, so product or a service, to increase a target metric, which in most cases is money, over time. Some examples, you can do dynamic pricing on different levels. You can do it on a global level with the example of the price for a movie ticket. So what's like the globally optimal price for a movie ticket? You can add additional information to the system. So what's the optimal price for a movie ticket on Monday at 9 p.m.? Or you can add even more information, making it more individual. So what's the optimal price for a ticket? It's 9 p.m. on a Monday and the customer is Bruce, for example. And the upper bound on how well dynamic pricing works in these cases, grows from 1 to 3. So from top to bottom. Yeah, and here a few additional details why this matters. So if you have static pricing, this example was for a chain that rents out hotel rooms and accommodation. And if you have static pricing in such a business, that means that, the room price is static, as the naming suggests. You can adapt the price, you can manually manage it, meaning that if there's a high demand for rooms or if there's little available rooms, you increase the price. If there's a lot of available rooms, you decrease the price. The idea with dynamic pricing is to do this in an automated way, basically trying to capture all this revenue under this line, demand line. And that's not the only benefit. The other benefit as well is that a reinforcement learning system can react to changes in the environment. And it can do that at a level that a human, even if you employ people to track everything news and change your price, it will never be the same performance. So it can take into account information like weather, events in the area, economic changes, in this case Corona, for example, and take all of that into account when optimizing the price for a room. And this is then what the whole diagram of the algorithm looks like. Here we have the algorithm feeding, all these data sources are fed into the algorithm, and it's actually training live. So people visit the website, see a price, they either book a room or not. That's the algorithm gets a reward, positive or negative, from that feedback, and essentially then adapts the price accordingly. The funny thing about this, and I don't know if you remember at the start, I mentioned being aligned with businesses when doing machine learning. So this is a good example of that, because one important aspect of reinforcement learning is exploration. So the algorithm may have the next best move already set up, but it may also choose to explore. Let's give a different price just to see what's going to happen in order to learn more. So that's called exploration. And in this case, the business that we were doing this for was not really aware of that. So what started happening while the algorithm was training at the start, some room prices were either ridiculously low or ridiculously high, which was essentially just a part of the training process. But they started freaking out, and what they did at the end is basically only allow the algorithm a certain spread of price. So basically, the base price that they have plus minus 20%. And that's an example where, you know, you need to make sure that if you're solving a problem, align with business, that they know what to expect. Because in this case, it would have probably been a better idea to just let the algorithm go for a few days and let it train, instead of limiting its movement in that way. And yeah, this is a few more details about the case. So we helped them increase the revenue, but the main reason why I added this slide was actually for you to have the link, so you can read about a bit more about it online. And yeah, so I hope this was useful for you. So we apologize a bit, you know, for the mess, and this is an interesting format to be doing this lecture in. Well, let's see, we still haven't saved it, so I really hope that Zoom saves it. otherwise, yeah, that would be really funny. Yeah, and special thanks to the colleagues that I think we also mentioned throughout the presentations, because, you know, we ripped a lot of the slides from some of their decks. And as Bruce already said, you know, if you have any additional questions, just reach out to us. We'll try to answer them as good as we can, or also, you know, put your comments on the YouTube video, and we'll check now and then and try to provide you more details. So yeah, that's it from my side.
Thank you, and good luck in your studies.
Yeah, good luck in your studies, exactly. Okay, now let's see.